All right, a little bit about the so-called normal distribution. This distribution, we haven't talked about specific types of distributions yet. We've talked about the frequency distribution and that table and that sort of thing. Well, the normal distribution is a special type of distribution, and it occurs naturally, I guess one way we could say it. It just occurs a lot in statistics, in life. As far as distributions go, it's one of the most frequently occurring type of distributions. And the kind of the distinction of a normal distribution from another distribution is that the normal distribution has what's called a bell-shaped curve. In other words, the graph of a normal distribution has the shape of a bell. So it's the bell-shaped graph or curve. That's the distinction to be made between it and other distributions. It's a bell-shaped curve. And so we get to draw several of these bell shapes. Now, of course, what we're talking about along the bottom here, of course, we got a middle there, but along the bottom is, you just have the values of your distribution or marks for certain ones of the values. But we'll talk about all this. Now, you might note here this is not a bar graph. It is a smooth, continuous, we would say, graph. And technically speaking, these lines out here, they keep progressing towards the line here, but technically they don't ever stop. I mean, the lines just keep going infinitely out there. I mean, it's not very wide out there, but anyway, obviously you can see, and then of course the height of the graph is kind of your frequency, how frequently occurring each value is. So just ask you this, which of the values on this graph are most frequently occurring? Where are most of your values at? Well, the most values would be in the middle, wouldn't it? There's a few values. There's not very many out here. The graph's not very tall, so there's not very many values out on the ends. Most of them are in the middle there, and we'll speak to that more in just a second. All right, but yeah, a couple of things about the normal distribution. Like I said, number one, it is smooth, and the other point is that it's symmetric. It's a smooth and symmetric bell-shaped curve. Now, what do I mean by symmetric? Symmetry. Symmetry just means same on both sides. Same on half of it, it's the same on the other side. So if I kind of draw a line down the middle, what this is saying is they're the same on either side. This side is the mirror image of this side, and vice versa. So it's the same on either side. Okay? I'll speak more about that in just a second. All right. Yeah, obviously there we have the highest points in the middle, and the highest point is in the middle, and it's the mean. Of this distribution. Highest point is in the middle, and the highest point is always that mean. I mentioned last time about the mean being the average, but another way you can think of the mean is it's kind of the balancing point. So if I was going to think of these as a weight, and I was going to balance it on my finger, I'd balance it right in the middle. So yeah, there's a number of reasons why the mean, the average has to be in the middle. But the mean is always in the middle, so we can always label that point in our graph in the middle. Okay? And then one other point is we're going to be talking a lot about percentages of values under the curve. Just point out here the total area under the curve is 1. Or 100%, okay? The total area under the curve is 1. And what we might do is break that up into the down the middle there. So what percentage would we have over here to the right of the mean? 50% on the right of the mean, 50% are less, yeah. And that's kind of what we're going to be focusing on. You know, you can think of the area under the curve in a lot of different ways. You can think of them as percentages. We could think of that as decimals. So we could say the area, this percentage, the percentage of value. So what this means, what particularly this would mean, 50% to the right of the mean would mean is that 50% of the values are more than the mean. That's what this would mean. %50 of the values are more than the mean, and then of course this would mean 50% of the values are less than the mean. Okay? So kind of make that connection between area and percent. Okay? This, we're saying this percentage is 50%. Or we could also say the area under the curve there is 0.5. Or it's 50% of the area under the curves, however you want to think of it. But percentage and area is the same thing. Now, let's say whatever distribution it is, if I were to ask you, if I were going to select one value from this distribution, what would be the probability I select one that's greater than the mean? What would be the probability I would select one that's greater than the mean? 50%, okay? So we'll also have a couple of problems where they ask you about probability, but probability is the same as percentage. So this area is 50% or 0.5, and the probability that a value is greater than the mean is 50% as well. So what I'm getting at here, probability of value is greater than the mean is 50% or 0.5. 50. Okay? So what I'm getting at here is if a problem asks you for area, it's going to be the same as it's asking for percentage or probability. Area equals percentage equals probability. Those are all the same. They're all asking the same thing. If we want to find a percentage, we want to find the area under the curve. If we want to find the probability of something happening for the normal distribution, we want to find the area under the curve. Okay, so that's going to be the name of the game. What is the area under the curve? Because they're not always going to be to the right of the mean or to the left of the mean. We'll use that some, but that's not what it's always going to obviously work out to be. So, all right, here's the type of question we're going to be asked. All right. Let's say I know this. Let's say from 7 to 9, my values, I've got, let's say that's 30% there. And then from 9 to 10, that percentage there is 15%. I'm just making those numbers up, in case you're wondering. But here's the type of question we're going to be asked to do. First of all, can you tell me what, I haven't told you anything about this distribution, what's the mean of this distribution? Can you tell me that? If this is a normal, the mean is 9, yeah. This is the mean. I'm kind of going at this problem backwards from what we usually do. I'm giving the graph. You'll supply the graph on these regular questions. But here's what we're going to be. Say we know that these percentages. What does this 30% mean? That means there's 30% of the values between 7 and 10. Right? I mean 7 and 9. You with me on that? Whatever these values are, and that brings up another point. In a normal distribution, we have been working with distributions where you can get 1 and 2 and 3. Some of them have decimals, but please note here on the normal distribution, you can get 7s, you can get 7.1s, you can get 7.2s, you can get 7.25. You can get, theoretically, any value, decimal, fraction-wise, any value is possible on a normal distribution. In other words, you're not just limited to 7, 8, and 9, and 10, and 11, 12 here. You can get 7.1s and 7.2s. It's a continuous distribution, meaning the values, you don't just get fixed number of values. So anyway, that's kind of a side point. But do you see what I'm saying here? Since this area here is 30%, 0.30, then that means 30% of the values are between 7 and 9. What does this mean? 15% are between 9 and 10. Okay? So if you understand that, that's kind of what we're So 15% are between 9 and 10. Okay? So if I were to ask you what percentage of values are between 7 and 10, what would you tell me? Add them up, yeah. Yeah. Since I know 7 to 9 is 30%, and I know 9 to 10 is 15%, wouldn't the percentage of values between 7 and 10 be 30 and 15 added together? So that's kind of the idea we're going at here when we're doing these problems. Okay? With a few twists, of course.